All right, let's talk about this. There's a new physics paper making waves, and you might have seen some pretty big headlines about manipulating gravity. It's a really complex idea, so what we're going to do here is just calmly break down what this one paper actually says, sticking only to what the author wrote. So this is probably the question you've seen floating around. I mean, after LIGO had that incredible success detecting gravitational waves, it's only natural to ask, okay, what's next? Is that next step really controlling gravity? That's the question we're going to get to the bottom of by looking right at the source material. And this, right here, is the key to the whole paper. The author, Ralf Schützhold, actually starts with this very analogy. He compares where we are now with gravity to where we were with electricity back in Benjamin Franklin's day. Franklin's kite experiment wasn't about controlling lightning, right? It was about moving from just watching it to actually interacting with it, and that's what led to the lightning rod. This really frames the paper's true ambition perfectly. Okay, so here's our roadmap. We're going to start with that lightning rod idea, then dig into why it's so unbelievably hard to interact with even a single graviton. Then we'll look at the experiment itself, what the author calls an optical Weber bar, and we'll check out its potential, and just as important, its limits. And finally, we'll see why physicists are actually so interested in this idea. Right, so after LIGO's Nobel Prize-winning work, the physics world is kind of in the same spot electricity researchers were a few centuries ago. We've proven gravitational waves are real. We can see them. So the next logical step, the next frontier, is to see if we can poke at them on purpose, to build our own lightning rod for gravity. But before we get to the proposed solution, you really have to appreciate just how massive the problem is. I mean, why is gravity so famously, so stubbornly hard to work with in a lab? Well, the whole challenge, which is almost impossible to wrap your head around, really boils down to one very, very small number. And this number, well, this is the whole problem right here. This is Newton's gravitational constant, g. The fact that it's so ridiculously tiny tells you exactly how weak gravity is. You need things the size of planets or stars to really feel it. So you can imagine, on the scale of a lab bench, its effect is just almost nothing. And because gravity is so weak, trying to make a gravitational wave in a lab, say by spinning something really heavy really fast, it's not going to work with the tech we have. The paper is really clear on this. Even using our most powerful lasers or machines to try and create a wave from scratch wouldn't even come close to making a single detectable quantum of gravity. So what is this quantum of gravity? We call it the graviton. You know how light is made of particles called photons? Well, the theory goes that gravitational waves are made of these gravitons. Now, it's super important to remember, and the paper says this too, gravitons have never actually been found. This whole proposal is built on the assumption that they exist, which, to be fair, is a pretty standard assumption in theoretical physics. And this is where the paper gets really clever. It completely sidesteps the impossible problem of creating a graviton. Instead, it asks a much smarter question. What if we took a gravitational wave that's already out there, one from a black hole merger that's passing by Earth anyway, and could we design an experiment that forces that wave to either give us a graviton or take one from us in a way we could actually measure? And the paper's answer is this theoretical proposal, which the author calls an optical Weber bar. It's a really smart design that would use light to interact with that passing gravitational wave. And to be clear, this is a blueprint. It's a detailed plan for how you could build this thing, but it hasn't been built yet. So this is the actual sketch from the paper. And yeah, it kind of looks like LIGO, but the way it works is critically different. The basic idea is you take a laser pulse, you split it in two, and you send those two new pulses down different paths right through the middle of space-time as it's being stretched and squeezed by that gravitational wave. Okay, here's the play-by-play. You split a laser pulse. One half goes down the x-axis, the other down the y-axis. As the gravitational wave comes through, it stretches space in one direction and squishes it in the other. This makes one light pulse steal a tiny bit of energy from the wave, while the other pulse gives a tiny bit of energy back. Then, and this is the magic trick, you send both pulses down a really long racetrack, and that tiny energy difference slowly builds up into a measurable timing difference, kind of like two perfect clocks that slowly drift out of sync. And this, right here, is the real game changer. In LIGO, the time the light spends inside the wave is the same as the measurement time. But this new idea separates those two things. The pulses only touch the wave for a split second. But after that, you can bounce them between mirrors for a long time, maybe for seconds, traveling millions of kilometers. This long accumulation time acts like a giant amplifier for that tiny energy shift. It's a huge potential advantage. Okay, so what does the math actually say? The paper runs all the numbers for this setup, and the results, well, they look pretty good. But this is probably the most important part of this whole explainer. We have to be super clear about what the paper is claiming, and just as clear about what it says we can't claim. So, the theory suggests this setup could be sensitive enough to spot the effects of a gravitational wave with an amplitude, that's the h value, of about 10 to the minus 22. Now that's great news, because that's exactly the strength of the real signals that LIGO is already picking up from space. So on paper, the idea is solid. It's in the right ballpark. But now for the crucial reality check, and this comes straight from the author. First off, this is a proposal. It's a thought experiment, not a real result. Second, it does not create gravity. It needs an existing wave to fly into its, quote, kite. And third, and this one's a big one, even if you built it and measured this energy shift, the author specifically says this would not be definitive proof that gravity is made of gravitons. It would fit with that theory, but it wouldn't prove it. So, if this thing doesn't make tractor beams and it doesn't even prove gravitons exist, then why is it getting any attention at all? Well, the real value of this idea is way more subtle, and honestly, for a physicist, it's way more exciting. So, the real question this helps us ask is, what could an experiment like this teach us about what gravity is at its most fundamental level? We're moving past the sci-fi applications and into the really deep, really strange territory of quantum mechanics. And here is the heart of it. A setup like this, at least in principle, could give physicists a way to test if the gravitational field itself can be in a quantum superposition, which means being in two different states at the exact same time. That is one of the biggest, most central, unanswered questions in the search for a theory of quantum gravity. To do that, the paper suggests using these really exotic types of light, called non-classical photon states, things like NOUN states. Think of them as specially engineered quantum states of light that are incredibly sensitive to tiny changes. Using them wouldn't just boost the signal, it could actually entangle the light with the gravitational field, giving us a direct window into gravity's quantum behavior. So let's circle all the way back to the beginning and answer our question responsibly, using only what's in the paper. What can we actually say? We can say that a physicist has proposed a really clever, new theoretical tool. It doesn't control gravity, but if it could ever be built, it might be the thing that takes us from just listening to gravitational waves to actually touching them. And in the process, it could become a powerful new way to explore the deep, quantum secrets of gravity itself.